Okay, 460, let's do this again. I apologize for the video and audio being out of sync last time. What I'm going to do is walk through again how you start with the files that I've provided you for the tramelblaze, and then create the memories necessary to utilize the tramelblaze. And then I'll show you how to run a simple simulation and get a feel for how you can debug your designs that are based on the tramelblaze, utilizing the list file showing how the simulation is actually executing your code. So the first thing I want to do is open up a new project. So I'm going to call this guy TV Start, tramelblaze Start, and I'll put it in the folder tramelblaze Start. And it's all set up for my Nexus 4. That's okay. So away we go. Now that we've got the project set up, let's go ahead and add the files to the project. So what we're going to add is we're going to add the test bench, we're going to add a top file, and we're going to add the engine itself. The memory we have to generate once we've loaded it. So let's go ahead and select these guys. They're added. If I look at them, my top file is how you interface to the tramelblaze. So all the ports are just the ports that you see on the top of the PicoBlaze. But inside, you see that there's also an instruction and an address bus. The processing engine corresponds to these signals, but it also needs to access the instructions to execute. So these are used to interface with the raw memory that we're going to generate. So we're set up. Let's just take a little bit of peek at our test bench. At the test bench, we instantiate the tramelblaze. Notice there's no address or data because it's hidden inside. And the interesting thing about instantiating a processor is really the only signals you need to supply it in order for it to start running is a clock and the reset. Once you turn off reset and your clock's running, the processor will begin to fetch and execute instructions. Now in this case, we want to simulate some external logic around the tramelblaze, and in particular it will be the interrupt. So what I've done is I will, in my test bench, generate an interrupt 10 times. I'm going to wait a microsecond, then set the interrupt. Then I wait for the tramelblaze to respond with an interrupt acknowledged, then I clear the interrupt. So I'll do that 10 times. We should be able to see the tramelblaze responding to the interrupts and then executing the interrupt service routine. So the first thing we need to do is generate our memories. So before we do that, let's just take a peek in our folder. In the assembler folder, we need to have taken the TBA file. So let's take a peek at that. I'm going to change the font just to make it a little easier for us to read. So I'll make it Courier New 14, and that should make it big. So now in our code, let's just walk through the code so we all know what we're looking at. It shows how a tramelblaze assembly file is created. Clearly, a semiconductor starts a comment, so the rest of that line is ignored. I want to declare constants for my coding, so I use the assembler directive equate. So I set up a label in column 1, and on the right hand side I define the value that I want to be substituted for the label on the left when it's encountered in the code. Anytime there's a constant value, the assumption is it's a hex value. Or any 16 tick H required. Constants encountered in the assembly of code are assumed to be hexadecimal values. Then with my start, I begin the actual executable code. So let me add that comment. That would be a nice comment right here. So I want to now begin the executable code. And so I start off enabling my interrupts. I initialize my registers. Then I enter my main loop. Most of these embedded processors have a main loop where it's just waiting. We'll talk more about this in future. But for now, we come up, we run in the main loop, incrementing our 0. Then what we do, we use the assembler directive, we change the address to 300. So here it defaults to address 0. So this code will be found at address 0. That, of course, is where the processor begins to fetch and execute instructions. Then at address 300, you'll find the code for the interrupt service routine. And here I'm reading the up, high, down, low bit and then making a decision whether I want to increment or decrement my register. Then I output it to the loadable register. Note in the code as delivered, I'm outputting to address 1234. So if we use the 4 LSBs of port ID to decode between one of 16 destinations, this will cause write sub 4 to be active because the output is a write. 4 LSBs, because the default is hexadecimal values, goes into the decoder. Write sub 4 goes high. Then, as I've mentioned before, it's the last 2 instructions in the instruction the vector into the interrupt service routine. So when an interrupt occurs, the processor will complete executing the instruction that it's currently executing, will then fetch the instruction at FFE and execute it. And of course the jump requires an immediate value to jump to, so the processor will utilize both of those words to execute the instruction. So that's our code. As we've seen before, I'll save my changes. When I want to run it, I'm going to run the Python file trambler. You need to have loaded Python onto your machine. You can find it at python.org. When you run it, it'll prompt you for the file that you want to have assembled. In this case, it's demo1.tba, and we can see with the date and time stamp that it updates the files. The file that I am interested in is the demo.list first. And why? Because this allows us to see where our processor is running when we are doing our debug. So inside of the list file, you can see the instruction address and the instruction content. So it turns out the enable interrupt is a one-word instruction. Load counter with zeros is a two-word because I have to define the load, the register I want to load, and the data I want to load in. So that's why it's a two-word, but the program counter continues. So the next instruction is at location 3 and so on. And what this will do, this allows you, when you run your simulation, we'll take a peek, you can follow along with the instruction address and verify how your code is running. Now I've tried to pretty print this as much as possible. It's not perfect, but if you get a list file with just a little bit of work, you can clean it up and have everything lined up so it's easier to read. So that's the list file. What else gets generated is the COE file. The COE file is the file that's used to program the memory. It's formatted according to the Xilinx requirements. Here, this corresponds to the first instructions at location 0. We then jump to 300. Then those are the instructions for the interrupt service routine. Then we can go all the way down to the bottom, and there is the vector for the interrupt service routine at FFE and FF. Format of the memory code, the TBA, the list file, and the COE file. So now let's go back, and we're going to say new source. And in the new source, we want to run the core generator. And the first one we're going to generate is TB-ROM. So let's go ahead and generate the code memory first. It's going to run. This is going to take a couple minutes. I apologize. You can fast forward if you want, but it will allow us to create our memories. As I've mentioned, you always need to create the TB-ROM every time you change your source code, but the stack RAM and the scratch RAM you should only have to do once. We want to use the block memory generator, and we'll say OK. It'll launch the block memory generator. Now we see it's TB-ROM. That's the instance name. If you want, you can see the ports. So if you look into my code, you can see how I've utilized these names on the instantiation of the memory. And of course, that would be the module name. In this case, we have to generate a single port ROM. And we want the depth to be 4096. Then finally, what we want to do, we want to point it to our COE file, which is in TB start, desktop, TB start, assembler, demo1, COE. He should like it. There it goes. I do a next just for fun. Then I tell it to generate. So now what's going to happen is the tool will generate the module for us. We'll see the hierarchy in the design window will recognize the ROM. Right now, if we peek up here, we can see that it's not there. So we'll let this run, and we'll see pretty quick. This will be resolved, and we'll see the little ice cream cone or little light bulb telling us that it's a module that they've created for us. It takes a moment. It doesn't really take too long, but it might be a minute, which isn't too bad. Everybody wishes it would run immediately, but this is much easier than the tramelblaze where we had to open up a DOS shell and then run the tools under DOS, then transfer them back to Windows. So it's going to run, and in a moment it's going to finish. And we see our light bulb. So now we've got our ROM memory. Now we need to generate the stack and the scratch. So we're going to repeat the process. New source, IP core. Let me move this down. So let's do the stack first. Stack RAM. Again, we want to use the block memory generator. We'll launch the block memory generator. Again, there's the ports on the symbol. We see our name is correct. We go to next. Single port RAM is what we want, so we don't have to change anything. The stack RAM is 128 deep. And now we can tell it to generate. So the code RAM is 4096 deep, stack RAM is 128 deep, and we're going to see the scratch RAM is 512 deep. Again, the stack RAM is used for subroutine calls where the processor needs to put the return address on a stack. It allows us up to well over 100 recursive calls. If you go over the 128, like I said in class, it'll break without any indication other than the processor will crash. So most of us, I think, will typically perhaps 3 or 4 or 5 deep is all we go. I'd considered perhaps adding some push and pop instructions where I'd push registers onto the stack, be able to pop registers from the stack, but I have yet to add that to the design. So there's the stack RAM. Now we want to add one more. We'll say new source again, IP core generator. This time it will be the scratch RAM. Always want to add to project. Next, launch the tool for us to generate the scratch RAM. Again, those are the names on the device. That's the module name that we instantiate. We want it to be a single port RAM. Now the depth will be 512. Say next. Now we'll generate the scratch RAM. So I hope everybody, if you're listening to this, that tells me that you are faithfully trying to follow along. What we're going to get when we run this, we'll have an environment that you can run a simulation before you do any Verilog coding at all. I encourage you to run a similar simulation as what I've presented on this demo because it'll give you insight into how the tramelblaze operates. It'll also, if you study the way it performs the inputs and outputs, you'll see exactly the timing, and it will help you when you go to design your own logic around the tramelblaze to ensure that you're able to communicate successfully with your logic. And the whole point of the tramelblaze is to assist us, to make it easier to do our design, to be able to offload to software tasks that without the processing engine we would have had to perform in hardware. So now we've got our environment set up. I like that. So now what we could do, let's go to our tramelblaze test bench, go to the simulator. Let's just make sure that our syntax is good, that I haven't introduced any errors. Now what we want to do is launch the simulator. Again, this is the simulation that'll run fairly straightforward. Let's go ahead, once this guy opens up, we're going to change what we see in the simulation to help us understand what's happening. So we get all the ports on the top level of the tramelblaze. Looks like it's still coming up a little. Oh, I want to get over here. So I'll move the clock up, move reset up. We have our out port IDs. Let's drop out port down. So we have our port ID, the read strobe, the write strobe, the out port, the imports. Let's put the import next to the read strobe, out port next to the write strobe. Then we'll have our interrupt and our interrupt acknowledge. Now I forget how long. I think this needs to run. So let me think about this. Was it 12 microseconds? Let's see what goes on. It may have been 12 milliseconds. 12 microseconds it is. So what we can see is the tramelblaze comes out of reset. Oh, and what I wanted to do, young people, is I wanted to come into the tramelblaze and I wanted to add address and instruction. And let me add a divider. So now this is inside the tramelblaze. And just because we want to be different, let's go ahead and change the color of these guys. I'll make them orange just for fun. Let's come back over here. Let me select them. Change the radix to hex to make it a little bit easier. We can then scoot this window over some so we can see a little bit more. Now I'm going to reset it and run it again. The first thing I want to demonstrate is when you zoom in, you can see the instructions. So let me go to 0. You can see that coming out of reset, so here it is, we're leaving reset. The processor has instruction 0 ready, and it fetches that first instruction and executes it. Program counter changes to the next address and again fetches the instruction and executes it. So these are the addresses of the instructions that you see in the .list file. These are the instructions that are being executed you see in the .list file. So if you get confused, you can follow along how your code is being executed by the simulation. Now the next thing I want to do is let's just look at the interrupt. So here we have the first occurrence of the interrupt. And I went a little bit too far, so let me zoom out. Let me scoot this over a little bit. Maybe this is no longer the first, but it's representative. So now you can see the interrupt occurs to the processor. It may take a handful of clocks. The processor has to finish executing the current instruction, store the return address on the stack, and enter the interrupt service routine. So the interrupt service routine was 300, right? So let's zoom in. Let's follow address, and let's see when we get to 300. So there is where we jump to FFE, FFF, then we went to 300. So you can see my engine's not totally clean, but we get there and away we go. So now we're in the interrupt service routine. So the processor itself generates the interrupt acknowledge for you. My test bench knocked down the interrupt. Now we can see in the code it does a read. The purpose of this read is to read up, high, down, low. You can see that it's a 2 clock instruction in that the port ID is held active for 2 clocks. The read strobe is held active for 1 clock, and I don't have my data source in this simulation, so nothing's happening here, but that would be the read of up, high, down, low. Now we want to see what the processor does next. So let me zoom out just a little bit. So we can see that in the interrupt service routine, the processor does the read. It has to go through and make its decision whether it's going to increment or decrement. Then it has to increment or decrement. Then it will come back and perform the output. Now the output is again a 2 clock operation. He has to provide the port ID for the write. In this case, he's writing to 1234. He has to provide the data that he wants to write. That should be output. and you can see that the right strobe is active on the second clock of the output cycle. So a lot of information contained here. It's to your best interest to make sure that you work through this example. Don't just watch it. Make sure you do what I've done. And as you play with this, it'll become more and more familiar to you. I highly encourage you to spend the time. You can either watch my YouTube video reading Pong Chu's chapter on assembly code. Make sure you study the instruction sheet, or better yet, read the PicoBlaze document describing the instruction set of the PicoBlaze. So I think we're ready to go. Hopefully everybody will do well. If you have questions, feel free to ask. So I'm going to stop here.